Chapter 9, Image Quality. In general, the image quality of a CT scanner can be described by several key performance parameters, which include high contrast resolution, low contrast resolution, temporal resolution, CT number, uniformity and accuracy, noise, and artifacts. We will begin by discussing spatial resolution. Spatial resolution describes the scanner's ability to resolve closely placed objects that are significantly different from their background. So, high contrast spatial resolution is when the contrast of these objects to their background is high. In-plane spatial resolution is when spatial resolution is measured in the XY plane of CT. The in-plane resolution is specified in terms of line pairs per centimeter or line pairs per millimeter. A line pair is a pair of equal size black and white bars forming a bar pattern. For example, a bar pattern representing 10 line pairs per centimeter is a set of uniformly placed comb-shaped bars with 0.5 millimeter wide teeth. The reconstructed image of a bar pattern is a blurred version of the original object due to the CT acquisition and reconstruction process being band limited. The high frequency contents are suppressed or eliminated. The edges of the bars are softened and the magnitude of the bar pattern is reduced. Still talking about in-plane spatial resolution, this is where spatial resolution gets a little tricky. I want you to refer to the text on pages 175 to 176 when trying to understand this next topic. Modulation transfer function, or MTF, can be used as part of the quality assurance to determine a scanner's resolution, capability, or used to compare the performance of different CT systems. And this is represented by a curve on a graph. Look at figures 9.2 and 9.3 in your book. So when a scanner, let's call it scanner A, can image more line pairs per centimeter at the same percentage of MTF as another scanner, we'll call that one scanner B, then this means that scanner A has better spatial resolution capability than scanner B. An ideal system would have a flat MTF curve, and this means that the object is reproduced exactly and is not blurred. However, this isn't practical. 3 points on the MTF curve are of particular interest, which are 50%, which is the frequency at which magnitude of the MTF curve drops to 50% its peak value, 10%, and this is where the frequency at which the magnitude of the MTF curve drops to 10% of its peak value, and 0% when the MTF curve drops to 0% of its peak value. There are numerous factors that affect the in-plane spatial resolution, but the main ones to reflect upon are the spot size and shape, the detector cell size, the scanner geometry, and sampling frequency. The scanner manufacturers mainly determine these factors, but us technologists do have some limited control of them. The in-plane spatial resolution is also strongly affected by the reconstruction algorithm. Remember that in Chapter 5 we said that the reconstruction algorithm involves two mathematical procedures, convolution and back projection. If the projection profiles are back projected without correction, blurring occurs. To sharpen the image, a convolution process called a ramp filter is applied to modify the frequency contents of the projection before back projection. The convolution algorithm, or the kernel, affects the appearance of image structures, and there are convolution algorithms developed for each specific anatomic application. In general, they are applied to emphasize soft tissues and bone. Take a look at figure 9.8 in your book to see how two of the exact same objects, which is a slice of a brain scan, are reconstructed from the same scan data with two different reconstruction kernels. The bone kernel produces a much sharper image, and as spatial resolution increases, the noise increases. Another parameter that affects spatial resolution is the reconstructed field of view. The reconstructed field of view, also known as the display field of view, refers to the diameter of the reconstructed area in millimeters or centimeters covered by the image. This is different from the scan field of view, which refers to the maximum size that a scanner is capable of covering. You often need to find the pixel size in regards to the field of view, since the pixel size is needed in order to reconstruct and visualize objects. A smaller pixel size with a reduced field of view means that there is better visualization of objects. Take a look at the bar pattern images from figure 910 in your book. The picture here shows what a bar pattern looks like on the picture on the right here, which is seen by using a phantom. Right here, this phantom. Cross-plane spatial resolution is when spatial resolution is measured in the z-plane of CT. Improved cross-plane spatial resolution reduces artifact caused by partial volume averaging. Cross-plane spatial resolution is traditionally described by the slice sensitivity profile, or the SSP. It is graphed as the intensity versus the location in the z-plane. Researchers use a small bead or a thin disc on a phantom when looking at SSP measurements. The disc is placed perpendicular to the z-axis and a series of scans are collected to construct the SSP. In many instances, the SSP curve is replaced simply by two numbers: the full width at half maximum, FWHM, and this is the distance between 2 points on the SSP curve whose intensity is 50% of the peak. And the other number is the full width 10th maximum, FWTM, and this is the distance between 2 points on the SSP curve whose intensity is 10% of the peak. One of the best things about CT when compared to radiography is its ability to distinguish low contrast objects whose density is slightly different from their background. So to understand low contrast resolution, you'll need to consider three tissues of different densities, which are fat, muscle, and bone, as well as their atomic numbers, which is represented by Z. Look at figure 916 in your book to understand a little better what I mean. The atomic number values of fat and muscle are too similar to be distinguished on regular radiography, so they will only appear as soft tissue shadows on regular radiography, but the contrast between bone and soft tissue is noticed because bone has a much higher atomic number than fat or muscle. But CT can image these tissues much better since it can image tissues that vary only slightly in density and atomic number. Low contrast resolution is measured with phantoms that contain low contrast objects of different sizes and is measured by low contrast detectability of the LCD of the scanner. And this is defined as the smallest object that can be visualized at a given contrast level and dose. From the LCD, we know that the visibility of an object depends on its size and contrast to the background. The CATFIN phantom demonstrates low contrast detectability, and it contains three sets of objects that are matching sizes located on different positions, usually on the 10 o'clock, the 2 o'clock, and the 6 o'clock positions on the phantom. Take a look at figure 917 in your book, but this image right here shows an example of the CATFIN phantom. The difference between the three objects is their contrast, so you can tell that this one right here has a much different contrast than this right here. And this one has a different contrast than this right here as well. Temporal resolution is a CT system's ability to freeze motion of the scanned object. This is similar to shutter speed on a camera. The high shutter speed is needed to reduce blurring effects caused by movement or motion. Awareness of temporal resolution has significantly increased in recent years due to the increased clinic utilization of cardiac imaging. So obviously with cardiac imaging becomes movement from the motion of beating hearts. One of the most challenging things to deal with when imaging the heart is the heart motion, since it is continuous and often irregular. There are a few different methods that improve a CT scanner's ability to freeze cardiac motion. The most straightforward way to decrease motion is to increase the scan speed. The third generation MS-CT scanners can rotate at speeds of less than 0.3 seconds per gantry rotation. And even at these speeds, though, freezing the cardiac motion is still hard to achieve, so reconstruction algorithms are needed and applied. Remember, the CT number is related to the attenuation coefficient of the object at hand. Because water is similar to soft tissue in terms of attenuation characteristics, it is important to establish its accuracy for CT scanners. And the CT manufacturers provide phantoms filled with water for this type of testing. When the phantom is scanned, the average CT number in the water portion should be close to 0. Linearity is another important parameter in CT image quality. Linearity is the linear relationship of CT numbers to the linear attenuation coefficients of the object to be imaged. This is checked by daily calibration tests when a phantom is scanned to make sure the CT numbers for water and other known materials are correct. If you want to see specifically what kind of other materials, there is a table in your book. It's table 9.1 that lays them out. When the average CT numbers of the materials are plotted as a function of the attenuation coefficients on a graph, the relationship should be a straight line if the scanner is in good working order. CT number accuracy is the accuracy of the reconstructed image values. The level of importance has increased with the introduction of dual energy imaging. And if you want to read more about this, take a look at page 186 in your book. Uniformity means that for a uniform phantom, the CT number measurement should not change with the location of the selected regions of interest or with the phantom position relative to the isocenter of the scanner. The CT number uniformity can only be maintained within a reasonable range, typically a few Hounsfield units. This is because of the effects of beam hardening, scatter, stability of the CT system, and other factors as well. Image noise is typically measured on uniform phantoms. To perform noise measurement, the standard deviation within an ROI of a reconstructed image is calculated. The formula is seen on page 188 of your book. However, most scanners provide tools to calculate the standard deviation over the ROI, so the use of the formula to calculate it is rarely required. The picture on the left here of the shoulder shows an image with noise, and the image on the right has little noise and is obviously clearer than the image on the left. There are 3 major sources that contribute to noise in an image. First, we'll talk about quantum noise. This is determined by the X-ray flux or the number of detected X-ray photons. It is influenced by scanning techniques, scanner efficiency, and the patient. The scanning technique dictates the number of photons that reach the patient, and the scanner efficiency determines the percentage of the photons exiting the patient that are then converted to useful signals. Number 2, the inherent physical limitations of the system, and this includes electronic noise in the detector photodiode, electronic noise in the DAS, scattered radiation, and many other factors. Take a look at figure 929 in your book to see an oval phantom with 2 different DASs while other acquisition parameters stay the same. You can see that a significant reduction in noise is seen with the lower DAS. The third major source contribution to noise are reconstruction parameters. A high-resolution kernel produces an increased noise level since it enhances the high-frequency contents in the projection. However, most noise represents itself as high-frequency signals and is enhanced at the same time. Noise power spectrum is obtained with the Fourier transform to break down the image noise into its frequency components. The standard deviation is not sufficient to fully characterize noise in an image, since noise in reconstructed images is no longer white. This image is an example of a graph generated when the noise power spectrum is graphed against its frequency. As we know, artifacts can degrade image quality, affect the perceptibility of detail, and even lead to misdiagnosis. Obviously, this can cause serious repercussions to the RADs. It can even lead to malpractice suits. An artifact is a distortion or error in an image unrelated to the subject being studied. A CT artifact is any discrepancy between the reconstructed CT numbers in an image and the true attenuation coefficient of the object. So basically, anything that causes an incorrect measurement of transmission readings by the detectors or an inconsistency between the measurement and reconstruction will result in an image artifact. Because CT numbers represent gray shades in an image, incorrect measurements will produce incorrect CT numbers, which will then produce various artifacts that affect the appearance of the CT image. Artifacts can come from many things. This includes the patient, wrong selection of protocols, reconstruction process, problems relating to the equipment, like malfunctions, and fundamental limitations of physics. We are going to focus on the most important artifacts that are seen in routine imaging in the CT world. Artifacts can be classified according to the appearance in the image, and then 4 major categories are then identified. We'll start with streaks, which may appear as intense straight lines across an image, and they're often caused by errors of isolated projection readings. The discrepancies are enhanced by the convolution process and then are turned into lines during back projection. Another type of artifact are rings and bands. They are produced when the projection readings of a single channel or a group of channels consistently deviate from the truth. It can be the result of defective detector cells or the DIS channel, deficiencies in the system calibration, or a suboptimal image generation process. These are mostly seen in third-generation scanners, and the ring pattern is formed in the back projection process from a defective detector channel reading. And I just wanted to lay out a few pictures here. The one on the left is the streak artifact, which you can see right in here, especially. And then on the right, we have the ring artifact. You can see right in there. 2 other categories of artifacts are shading and miscellaneous artifacts. So with shading, this often appears near objects of high densities. And it can be caused by beam hardening, partial volume averaging, spiral or helical scanning, scatter radiation, off-focus radiation, and incomplete projections. It is formed by the gradual deviation of a group of projection readings over a limited range of views. So the 4th one is miscellaneous artifacts, and this includes the basket weave and moire patterns. Patient motion artifacts can be voluntary or involuntary. With the voluntary kind, they are directly controlled by the patient, and this includes swallowing or respiratory motion. And the involuntary kind are obviously not under direct control of the patient, and these include head motion with injury, peristalsis, and cardiac motion. Both of these appear as streaks that show high contrast edges of the moving part. Motion artifact can even be seen when oral contrast moves in the GI tract, which is actually pretty interesting. To reduce, you'll need to immobilize the patient and use positioning aids to make them comfortable and ensure the patients understand the importance of holding still. Another method to reduce this artifact is to shorten scan time. Metal artifacts include prosthetic devices, dental fillings, surgical clips, and electrodes that are seen by streak artifacts on the image. The loss of information is seen by star-shaped streaks. Patient motion is often a major factor in order to reduce the appearance of artifacts. The blooming artifact occurs when the stents or other small metal objects bleed through to the neighboring voxels and make the object larger than it really is. And it can be reduced by generating images at higher KEV levels. The best approach, though, to combat these artifacts is to replace the corrupted projection samples with estimated projection samples. Images that are made with estimated projection samples are then usually free of artifacts. Beam hardening refers to an increase in the mean energy of the X-ray beam as it passes through the patient. And as the object size increases, the mean energy shifts higher because the lower energy photons are absorbed as the beam passes through the patient. This change in the X-ray spectrum leads to changes in CT numbers if proper compensation isn't made. Also, since radiation beams have different path lengths through an object, the X-ray beam spectrum becomes channel dependent. There is less beam hardening at the periphery of the object where the radiation path is short, compared to the center of the object where the radiation path is actually longer. Take a look at figure 938 to see an example of this. Due to the beam hardening effect, errors in CT numbers increase gradually from the periphery to the center of the object. Beam hardening effect is material dependent, so when dense bones or contrast agents are in the beam path, dark shading artifacts can occur because the beam hardening correction applied to soft tissue does not work well for bones. To combat this, iterative reconstruction helps. As we have discussed previously, CT numbers are based on the linear attenuation coefficients for a voxel of tissue. If the voxel contains only one type of tissue, then the calculation will not be a problem. However, if the voxel contains 5 different tissue types in which the CT numbers are close together, then the CT number for the voxel is based on an average of those 5 tissues. This is known as partial volume averaging. When the voxel contains multiple types of tissues that are very different from one another, like soft tissue and bone, then partial volume averaging can lead to partial volume artifacts. These types of artifacts appear as bands and streaks. These artifacts can be reduced with thin slice acquisitions and computer algorithms. However, partial volume artifacts can still occur with thin slice acquisition if special attention isn't focused on other accessories near the patient. And take a look at figure 943 on page 196 of your book to see how accessories can actually create the artifacts. Aliasing artifacts arise from insufficient projection sampling or from insufficient view sampling. To minimize these artifacts, the number of views or the number of ray samples per view can be increased. Also, the convolution kernel can be modified so that only certain frequencies are allowed into the filtered projection. In this picture of the thorax, the aliasing artifact is seen when the slice thickness is increased from 1 millimeter on the left side to the right side. And you can actually see the aliasing artifact right here. Noise-induced artifacts are seen when photon starvation occurs. Photon starvation can occur as a result of poor patient positioning in the scan field of view and poor selection of exposure techniques, scan speed, and limitations of the CT scanner. More photons means that there is less noise and a stronger detector signal. These artifacts are seen as streak artifacts, and to minimize these, the tech should optimize patient positioning, scan speed, and exposure technique factors to minimize the streak artifacts. They can also be reduced with adaptive filtering algorithms, and these algorithms actually drastically adjust the amount of smoothing operation on the basis of the X-ray flux level at each projection channel. By selectively smoothing only the channels that contribute to the streaking And by varying the degree of smoothing on the basis of the noise level of the signal, the tech can reduce the streak artifacts in the image and also preserve the spatial resolution of the image. Another type of noise-induced artifact is related to noise non-uniformity. And this is when noise within the reconstruction field of view is highly heterogeneous. It can produce bright and dark horizontal strips in the MIP or the VR images. And you can see an example of this in figure 947 in your book on page 198. This type of artifact can be reduced with either an improved reconstruction algorithm or an advanced image processing. Both of these methods create a more uniform noise pattern in the final image. Scatter radiation. This fundamental phenomenon is associated with the interaction between X-ray photons and matter. In conventional radiography, it reduces object contrast, but in CT, it produces artifact. It is controlled in the past. It has been controlled in the past by placing a post-patient collimator in front of the detector to reject any photons that don't follow the straight line path between X-ray source and the detector cell. This no longer works on multi-slice and volumetric CT scanners, so dark shading artifacts occur. Scatter-induced artifacts can be corrected with algorithms by carefully estimating or measuring the scatter distribution in the projection. Then the estimated scatter can be removed from the measured intensities. Cone beam artifact is complicated, so we won't get into it in depth here. Cone beam artifacts are caused by incomplete or insufficient projection samples as a result of the cone beam geometry of multi-slice CT.